Okay, so welcome everybody to today's meeting of the IFIMAC-ICMM joint seminars. It's a pleasure to welcome today Hugo Terças from Lisbon. Just to introduce him briefly, Hugo studied physics in Lisbon and finished his studies in 2007, and later continued doing a PhD there also in Lisbon. And after his PhD, he moved to France, to Clermont-Ferrand for a postdoc, later for a further postdoc to Innsbruck, where he worked on cold atoms. Then, since 2017, he was working as a research assistant again in Lisbon. And since 2 years, he works there with a grant from the CEEC in Portugal as an invited assistant professor, and that's his current position, where he's working mainly on plasmonics, where his interest is in hydrodynamics, nonlinear waves, and also quantum plasmas, today's topic. And his other topic is Bose-Einstein condensation, where he works on solitons and vortices and that kind of dynamics. Today, he will tell us about his research in plasmonics, to be specific, in plasmonic instabilities in 2D Dirac materials, which also connects to the interests of our institute. So welcome, Hugo, to our virtual seminar, and we're happy to have you here and to hear your talk. So please.
Thank you so much for the invitation. It's a pleasure to be here at the ICMM. It's always a pleasure to visit Madrid anyway. So it's if you can combine the nice stay in the city with the good scientific discussions and nice people around, it's always a good pleasure. So for youth who invited me, Tobias Staub in particular, and the other people who we have been discussing with, I'm very thankful for the invitation. I just want to share. I need your permission to share this.
Sure,
please. So, by the way, thank you also, Sigmund, for this nice introduction. It's very nice it was very generous from your side. Today we are. I'm talking a little bit about the work that we have been developing along the last, let's say, 2 years, I would say, in this field of plasmonics. We have a slightly different approach, probably, that is very inspired in the school of plasma physics. So although we are interested in these substrates or these materials that support that are typically solid state, we are more interested in doing this in the way with the tools that we know from plasma physics. That's our approach. And we hope that the community will perceive this in a good manner. The idea is really to understand how plasma waves in these solid state devices, including materials, in particular Dirac materials, happens to be can be described within these tools. And we want to see how far we can go. So mainly, I'm presenting the results containing these 4 topics. I will try to be brief, so I'm not interested in making you suffer much. So I will try to skip some of the details, and then if you are really interested, please refer to these publications here, and you can check the details. So in terms of what is the problem is really close to, or is well related to Terahertz problem, which is somehow part, I suppose, to this problem of harmonic generation in plasma and also in solid state devices. So Terahertz is a part of the gap that you want to fill. And we know that we have high power and low power solutions. High power solutions are very well known, but they are very bulky. So the idea is that the pretext for this investigation, let's say, is to try to understand if we can go towards low power Terahertz solutions with plasmonic systems. And it seems that eventually, yes. So, and then I will discuss a little bit about these electrically controlled plasma instabilities. Our approach is slightly different from what most of the community is doing. I suspect that are for what I understand, there are two sorts of way of doing this terahertz and high harmonic generation. One, you shine a laser on the systems and you see what happens afterwards. So this is probably one of the approaches. The other one is you will do it in electric injection. So we are really interested in electric only injection, because this allows your system to become more compatible with with integrated circuit technology. And this is exactly the goal. So if you want to be competitive one day in the market, you have to think about solutions that you can integrate easily in integrated circuit technology. So in particular, we are going to deal most of in this talk with the Dirac instability. I will then tell you the details about what it is about. The Dirac instability in graphene field effect transistor is a phenomenon that has been under intense investigation for recent years. And then I will try to discuss, let's say, how we can integrate more aspects of graphene physics, graphene and other 2D materials, to be honest, to be more general, to build these terahertz lasers. So that's pretty much the scope and pretty much the motivation of our research, and in particular of this talk. So you know the terahertz problem. You don't really have an introduction here, but I keep here for those who are not very familiar. So we have two branches. So communications happens mostly with electronics or photonics, and there is a gap here in the terahertz range between electronics and photonics in the 10 to the 12 the terahertz range, so 10 to the 12 hertz. And this is supposed to be mitigated. So this technology is supposed to be complemented with plasmonics. So plasmonics is really the field of physics that is going to support technology in the future of terahertz radiation. But the problem is that some materials block visible and infrared light. So the idea is that, but they are transparent to terahertz radiation. So this is why we are interested in terahertz at all, is because terahertz radiation are very important for some applications, especially for those materials containing lots of water, for which visible and infrared radiation is not transparent. So yet, the idea is to use terahertz radiation for materials for many applications. So some of the applications of terahertz is these biocompatible systems, because you can do terahertz spectroscopy of blood cells and bacteria. Other one, which is probably something that we can really try to put some effort on and really try to collaborate in the future with our medical doctor colleagues, because I think that this can be promising for non-invasive tomography of issues from one hand, and also for the treatment of some cancers. Because if you have some sources of terahertz, some sources of radiation for localized hypothermia that penetrates very few millimeters in your skin, you can treat some classes of skin cancers. So if you have some solutions for some terahertz, some sources of coherent terahertz radiation, so let's say terahertz lasers, it would be very desirable for medicine. So this is something that we have to keep on. We should keep on in our future, let's say, projects, or in the when motivating future projects in terahertz, we should probably keep a look in what are the interests in people in medicine and biology in general, because I'm really sure that we can find some synergies here in terms of applications. So the other application is concerned security, because it penetrates, terahertz radiation penetrates clothing and planting without damaging. So the idea is that in principle you can do this kind of security. So this is, let's say, the motivation why we do terahertz, and why terahertz is still a very interesting problem. And this is for sure something that you are very aware of. Some solutions. Well, we have very brilliant high power sources for terahertz that are produced in these cyclotron facilities. So if you accelerate your electron beam that is relativistic, at certain point you have some terahertz pulses that can be excited or can be extracted from these accelerations. And of course, these pulses are very energetic and you can eventually use. They are not very coherent, but still they can be used for some applications. Well, but these are very high power. They are not tabletop. You cannot transport them, so they are not desirable. They are too bulky and too intense for most of the applications that we are interested in. Another solution, and this comes with the low power sources, to be fair, we have to acknowledge they exist, those based on quantum cascade lasers. Quantum cascade lasers can in principle also produce this terahertz radiation, and eventually they can produce some radiation that can be then used for terahertz applications. Well, this is another solution. But in general, quantum cascade lasers operate at very, very low temperatures. So we have another problem. You have a system that is low power. Okay, so it emits low power terahertz radiation, which is probably something that you can use, but it's very, very hard to operate because you have to keep the machine to cool it down. So if one source is very bulky, the other one becomes bulky for a secondary reason. So what about integrated circuit technology? So the idea is they are desirable for terahertz detection because if you have a chip, a microchip, let's say a waffle, you can do you can produce some scheme, you can organize some schemes where you can detect terahertz radiation in tabletop scales. So they are scalable because if you do this with integrated circuit, it's more or less cheap. So you can integrate this, and even if a single module produces a very, very tiny amount of power, if you do a thousand of them in a chip, you can have a reasonable power afterwards. So, and they are easy to interface with biosolvents and so on. So there are lots of reasons why we should exploit integrated circuit technology. And this is where people from condensed matter and solid state communities kick in because they really know how to manage these things. So the terahertz problem now is is a problem of the communities of solid state physics and condensed matter physics. So then the problem is, if you want to do this kind of schemes in the integrated circuit technology, we have to think that, well, this is probably very hard to shine a laser here in this system and then use the excited waves or the waves that are produced by these lasers and then capture the radiation produced by it. So we are interested in doing this all electronic. So the idea is to excite plasma waves in these solid state devices, in particular field effect transistors, because with the gate voltage we can control the Fermi level. And this Dyakonov-Schur instability is an instability that is very similar to this Scholling instability in shallow waters. So it's very similar to what happens here in this picture. You have some velocity here, and because of the gradient of height, you have the wave breaking, but they have constant feedback. You have constant feeding of water. It becomes at a certain point what you have is growing and breaking of this wave. So there is a dynamical instability in the shallow water modes. Very inspired by these mechanisms, Dyakonov and Schur themselves, they proposed in 1993 a mechanism that is very similar to that happening with electrons in graphene. So the idea is that what we have to do is just produce the similar for electrons of this Scholling effect. So if you do constant density in one hand in the source and constant current in the drain. If you are able to produce this asymmetric boundary conditions, you produce some very fancy instabilities here in the system, and it's all electric. So you don't really have an external electromagnetic field. It's purely electrostatic. Okay, so this is a good part of it. Well, the problem is that in the original proposal done with semiconductors, high mobility semiconductors, yet they were high mobility, but the mobility was not good enough to allow the stability to grow, because this instability mechanism is somehow a coherent process. So you have to understand that the modes grow by feedback. So these feedback mechanisms, the mechanisms allowing feedback, are coherent. So if you have some losses in your system because you have phonons kicking in, or you have impurities, especially impurities in the system that contribute a lot in this kind of semiconductors, you have killing of this instability. So it has been, these mechanisms of this described in the 1993 paper by Dyakonov and Schur remain elusive for many years. And also with the advent with these high mobility materials, such as the Dirac materials, which graphene is probably one of the most celebrated ones, there are some hope again for this kind to observe this kind of instabilities. And the idea is that we can use really, making this short story long story short, you know exactly what happens, so I don't really have to tell you what's going on. Near these K points, you have these Dirac cones, which described by these local Hamiltonians at the single particle levels. And the idea is to put this Dirac cone here in this field effect transistor configuration. So you now have a gate, you have your graphene here with the Dirac point, and you can control now the Fermi level with this gate, and now we have your field effect transistor. So this is, let's say, under the technological point of view, the advance with respect to the technological advance that is now allowing and renewing interests around the Dyakonov-Schur instability. Okay, the thing is, electrons are not free carriers. They have Coulomb interactions, and because of the Coulomb interactions is where these plasmons kick in. So we have electron-electron interactions, and these electron-electron interactions will allow for a collective response of the electrons that will be the plasmons, right? So and then we can control these plasmons in this configuration. So I think that this is very familiar for you. I'm not really saying anything new. So what are our approach? Under the technical point of view, what we are doing is just we are organizing, or we are making the description of the transport description of these electrons with interactions in terms of Boltzmann equation. So this is the semi-classical approach. Then I will tell you a little bit about a more quantum approach. But the semi-classical approach allows you to write a simple equation like this, where your velocity now is just the velocity, the Fermi velocity of the band along the direction of propagation. Then you have also these interactions and eventually some collisions that you have to put in. So now, depending on the contributions of the collisions, you are either in the kinetic regimes or collisionless regimes, or in the hydrodynamic regimes. But with this in mind, you can compute the momenta. So you can average over the phase space distribution function. This F is a function that is defined in K, R, and T, so in the phase space. You integrate, you do these partial integrations, and you recover the density and the fluid velocity, something that you're also very familiar with, for sure. Well, this allows you to construct some hydrodynamic model. This hydrodynamic model for graphene now is slightly different from, and this is the part that I would draw your attention to. Usually would recognize this term here, right? This is the usually convective term that you have in usual hydrodynamics, for example, classical plasmas. What happens is now we have this extra term here that comes exactly from the fact that you have these bands here. Okay, so the fact of having something that is non-parabolic fluid allows you to have implications already at a semi-classical level, if in the kinetic term. This is very, very profound, and you'll see in a while. You will see. I'll show you in a while one of the consequences of this. So these extra new terms that appear in the hydrodynamical equations, that some people in the community are not really taking very serious for some reasons that I really don't know why. Probably they don't think it's important, but this extra term here will correct many of the things that we have here, namely the thresholds for instabilities and stuff, right? So this is something that we have to keep on. On the right hand side, we just have the source terms, the force terms. So from one side we have the electric field that you can, if your system is ungated, is just the electric field produced by unscreened electrons. And have the pressure here, which is the Fermi. Basically, if the Fermi level lies well above the neutrality point, you can say that TF is much larger than the room temperature, and then you can approximate the pressure to the diagonal pressure, which is the Fermi pressure. Right? So for this configuration here, the graphene effect transistor configuration, what we consider now is the following: motion along this X direction here, for example, motion along the X direction, and so we can go for a, let's say, one-dimensional version of this for you to understand what's going on more explicitly. So those are the explicit terms. For the in the gradual channel approximation, we say that the electrostatic potential felt by the electrostatic energy, felt by the electrons is given by this. So this D0 is the distance between the graphene sheet and the gate. N is the local density, which is a function of space and time now, and epsilon 0 is just dielectric permittivity. The same stems from the quantum pressure, so you see that it depends on the electron density here, and also on the Fermi velocity. So this is the usual quantum pressure that appears here. So these things here allows you to recover the results that you know from RPA. So if you compute the dispersion relation of plasmons in this configuration, you get the same dispersion relation that you would get from RPA. So in principle, it's consistent what you know. So at the linear level, let's say, you get exactly the same response as you should. So at least this is consistent with RPA at the linear level. But we are interested really in the nonlinear response, so later times of these waves, because if we have instability, you have growth. So let's come to this. So again, in this configuration, so now focusing on in this work, we are mainly interested in the gated case. Okay, so then we can discuss eventually the ungated case. But for the gated case, so the screened, where this potential is given locally, has a local relation with n. Otherwise, it would be a non-local relation with the density. What you get is this kind of dispersion relation. So you do the linear perturbation analysis. So you make N0 is the local density produced by the gate. So by setting your Fermi level, you fix the value of N0, and you can also do a source to drain current that allows to fix the value of your velocity. Okay, so this is the configuration that you have here. And this is, let's say, the engineering perspective or the circuit perspective of this that allows to do this kind of configuration. And you get this kind of dispersion relation. So this is the dispersion relation with the shift, with the global Galilean-like shift. It's not exactly Galilean because you don't have Galilean invariance in this system. But you see here that you have two modes, these two modes here, and they lie fortunately above the continuum. So in principle, you can excite these plasmons without undergoing damping. This is good, the good part. So you don't have intrinsic damping in the continuum. This is something that you have to avoid, otherwise you will kill your instabilities, right? Just in this instability is just by, let's say, killed by the statistical physics, if you want, of the problem. Is not even the purest system that you can produce would not even allow you to excite a plasmon if these lines would go inside the continuum. So this is good news. Even for the gated plasmons, the slope of these dispersions lay above the Fermi, the continuum. So the Fermi velocity, so the velocity, the group velocity of these modes are the phase velocities of these modes are larger than the Fermi velocity, which allows you to produce these plasmons. Okay, we have these two modes, and now you ask, what can we do with these two modes? And that's the idea of doing of the Diakonovsky instability. So let's imagine that you look for a certain energy level, you look for what are the fluctuations of the wave vectors that you can produce. So you have two here, right, for a certain omega. So if you invert this relation here for k, and for k, so you solve for k instead of solving for omega, and you get these two k plus and k minus given here, right? So they are not the same. So there's a difference because of this shift of the velocity, there's a difference for the waves that go in one direction and the waves that go in the other direction. And this is important because in this exponential here, it will be non-zero, right? So if you impose the symmetric boundary conditions, so now we say that the source n is fixed by some constant some tension, let's say, and here by some current source, you can fix the value of your current by doing this asymmetric boundary condition and using this dispersion relation. What you can check is this is the condition, right? So you get this condition for the omegas, right? So not all omegas are allowed, but only the omegas that fulfill this relation here, and this is imposed by the boundary conditions. If you solve this, you get this Dirac-Schur instability. So your frequency acquires imaginary part, and this imaginary part is given by this. So this is the 3/4 factor here is what differs exactly from the classical part in graphene, because of this 1/2 that we get here in the hydrodynamics. Okay. So you see that there's the small deviation from the, if you compare this to the original paper from Dirac and Schur, you have this small correction. So in what about comparison with the simulations? You can see here, so those lines are the solid and dashed lines are the results for of the analytics for different values of V0 over L. Also for different values of this typical frequency, if you want, or nominal frequency of the system. And you can see here also for the same thing for the growth rate. So gamma is the growth rate of the instability, right? The rate at which the instability grows in your system, or the gain, if you want. So this is as a function of S. So I didn't mention what S was, sorry, but S is just the local velocity that appears here in the system, and this given in terms of the parameters of your gate. Sorry, if I should have put some expression for that. And you see here that's the interesting part. So here are the analytics, and these results here with the open circles are the results that we extract for a certain gamma of parameters, exactly for the parameters of this purple line with numerics. So there's a good agreement with the numerics. And the good part is that even the numerical results lay well above the 1/tau. So the typical gamma or the scattering rate due to impurities in graphene. So for example, these values here have been extracted for suspended graphene. And you can see that even for moderate values of S over 0, you can already see that this gamma lays well above this threshold for the impurities, right? Because otherwise, if this quantity below this let's say this shadowed region here, you don't have instability for the reasons that we mentioned before in the semiconductors, right? So that really imposed boundary limitations in the Dirac-Schur, in the early observations of the Dirac-Schur instability with high mobility semiconductors. But here, fortunately, for the parameters, they entrust us. You can trust us that these parameters are realistic. You can see that we can eventually have some hope to excite these plasmons with electric injection. So, just to make the point, we are having a gated system. We are just putting a current, making some boundary conditions, and we are producing an instability of the mode. So now the electrons are bouncing from one side to the other and growing in amplitude. Of course, this is the linear analysis. So we have to go to the nonlinear analysis to understand what's going on. Nonlinear analysis is done by including all the orders. But what we do a little bit better. We do direct numerical simulation. So we just put these hydrodynamical equations in the computer, and you can check the details of this code here by Terças. Is the code developed here by Pedro, and you see exactly the message and you can see exactly the message that you wanted to convey. So initially you have exponential growth of the amplitude of the wave, and at a certain point, because of the nonlinear nature of the hydrodynamical equations, you have the saturation of the instability, right? So at later times, your intensity, this is an intensity take, let's say, at the middle point of your channel, okay, just for you to see what's going on. We could plot the whole thing, but you couldn't see very well. And you see that in this, the intensity, also the density wave, let's say, grows in time, and at a certain point it saturates, and this is what behaves. So you can, already looking here by eye, even before doing the Fourier transform, you can see that at late stages, your signal is very, very clean, is almost sinusoidal. This is very good because in principle, the radiation emitted by this is very coherent. So this is something that we have checked. We have calculated the spectrum from one side. So you see the spectrum here is really these are harmonics. So you have the first harmonics, second harmonics, third harmonics, and the other ones that they start to die. So the signal is extremely pure in terms of spectrally speaking. And then we also calculate the far field electromagnetic field using the IFIMAC-ICMM integral. So you can, once you know the currents, the local currents and the local densities that you have in the system. So you can save this in your simulation, make an array, and then you can reconstruct the electromagnetic field in far field. So you can really see what's going on, how this antenna radiates, right, in the terahertz range. These blue lines here, just for the record, is the power emitted if you do, instead of doing a DC experiment, you do some pulses. So you do some pulse signals, you send some pulse signals in the gigahertz range, and you see that instead of having this beautiful spectrum, what you have is this terahertz comb, more or less, right? So the spectrum becomes a little bit more is Gaussian, because of course this width of the spectrum is associated with the direction of your pulse. Okay, so depending on the applications that you want, you can either go for DC or AC situations. So the other thing that you wanted to evaluate at a certain point was the coherence of this signal. So far we are doing this classically. So what we do is to calculate the G2, the G1 function, so the autocorrelation functions either in time and in space, so from this field that you calculated far field. Okay, so we calculate the field in far field, and then we evaluate for these quantities here. You see, well, for moderate values of these, for reasonable values of the parameters, let's say S over V0 is over 10, which means that the V0 is the velocity of the fluid, okay, which it's well below the Fermi velocity, as should. Typically speaking, we are always talking about no more than 20% of the Fermi velocity. And S over V0 is around 10, is also a reasonable value. So it's something that you can get with regular gate tensions in your system before burning your circuit. And you see that the coherence that you get is not very, very bad. So it's not the correlation is quite, well, we can say that it's quite good depending on the parameters, right? So this is the correlation that you can get over time. So the correlation is also good, which is something that is important to characterization of your radiation, right? So if you want to say that the radiation that you have is coherent, or you are looking towards a laser, you really have to pay attention to these quantities. Of course, there are other indicators that you have to calculate, but so far we anticipate that the radiation that we have is essentially classical. So we are not talking about a quantum emission. So we are very, very far away from single photon emissions with this scheme, as far as we understand. So we should not worry about let's say quantum indicators for these things like the Fano factor or something. So in principle, we can still rely on this classical to semi-classical characterization of the radiation. So this was, let's say, the first part of this talk, characterizing this instability, how we investigate, and how we can which are the quantitative features of these things. So this is for us, it's a little bit, it's promising. It makes sense. It at least tells us that we have room to improve over the semiconductor physics. So in principle, this graphene, in particular graphene, can be in the run for the next generation of integrated circuit solutions for terahertz based on this Diakonov-Schur instability. Just another aspect about this radiation pattern is, if you do the angular pattern of this, you see if you have a regular dipole, this is the distribution, the intensity chart, if you want, for this radiation. So the usual dipolar thing, so with a single electron emits with the square of the cosinus in this blue line, and for some reason, this is something that we don't really know yet. In the case of graphene, it's really similar to the cosinus of the theta of the polar angle. So the aperture of your radiation is a little bit larger than that of a single dipole. And you see here so the dots are the results from the simulation after the construction of the electromagnetic field, and you see that it's very, very close to cosine of theta. Well, this is something else. Is also a particularity of this emission. So if you look at these field effect transistors as an antenna, this is really the pattern that is very similar to the one of the dipolar antenna, but is slightly different in terms of the behavior, in terms of the quantitative behavior. Of course, it doesn't offer extra lobes. We don't have extra lobes in the radiation because of the nature of the motion itself, but quantitatively slightly different. Well, there is another problem, is that this is good for suspended graphene, but if you go to encapsulated graphene, in principle you could have a problem. How and the reason is because when you have graphene in contact with a substrate, this the scattering rate increases, so you have collisions with the impurities and phonons of that substrate, and this may kill a little bit the thing. So how we solve for that? So we did the following to overcome this problem. What we did is, instead of having a constant velocity, local velocity of the system, what we change is the dielectric permittivity of the material. So you do a gradient in the material that is below your graphene sheet, and we do, for example, linear gradients. This alpha is very small, so it's just very tiny gradient. We hope that some experimentalists can eventually do this one of those days by doing a grading in your epsilon. And if you do this, you see that the instability increases a lot. So the gamma, so the growth rate of instability increases a lot by just with a very tiny gradient in your substrate. So imagine that, for example, that in this configuration here, the growth rate in this red line lays below this scattering rate with the impurities. Well, this would correspond to a system with no instability. But now, if we can increase this gamma with this trick here, you can in principle overcome this thing. So this is a more or less a practical trick, let's say, to overcome the problems that when you go to encapsulated graphene situation. This is something that we still don't have any kind of experimental estimate, because we really don't know how realistic this is for this value. This is very low, so in principle this could be possible, but it's something that in principle we could discuss with you here at the ICMM. Probably you know some knowledge about these materials and how you can produce these materials in practice. Well, if you are interested in full electronic terahertz generation, in principle, you could also think about a situation when you have not only one, but a second one here. So instead of having only one graphene, now you start to do, you put another one and you feed this with omega 0. So the idea is that, imagine about terahertz harmonic generation problem. In a harmonic generation problem, you have a nominal value that you put in, and then this nominal value emits other or creates other frequencies for nonlinearity. The reason why this is something usually done with this is something that you can do with lasers, right? Because lasers you can produce signal. So you can use this first diagonal of instability to produce a DC electrostatics oscillating electrostatic field in the terahertz range. So this is the new part, because so far we didn't have any source of electrostatic field oscillating the terahertz. So now we can have, and we can inject this, so we can use a buffer. This buffer is something that prevents the signal to come back here and allows to go in one way only. And then we are analyzing now in this yellow. This is what we are analyzing in this yellow, the second in the second circuit, so in the second field effect transistor, what is happening. So you can see here, this is the spectrum that is produced after this injection, and you see here the generation of these harmonics because of the injection of this first harmonic. So it's with the second harmonic generated, third harmonic generated, and other harmonics here. So this is the linear feeding. And we came with another solution. This is something that we are now investigating. And these days here, talking with Rui, we came with this solution, which is that, well, instead of doing this in the linear case, we just do a feedback loop. So we just get this thing and do a buffer, and with the summated signal, we put it back in your system. And you see that, you probably don't see like this, but if I do it very quickly, you see that there is a growth at least of 1 order of magnitude in the third harmonic generation. So the second harmonic generation decreases a little bit and gives energy away to the third harmonic. So this is something that we are currently investigating, but we are very excited about this because we can do third harmonic generation or third harmonic amplification in that case, just with this feedback loop. And this is all electrostatic. We don't need any external laser to do this. So we are very excited to see how far we can go with these schemes here. So just based on these electrostatic oscillations in your graphene. Well, what about magnetized plasmons? We, at certain point, we're also interested in understanding what happens when you add magnetic fields, because discussing with Pedro, we were interested in this whole problem and the whole currents, and we came with these magnetic fields. So let's say we investigated, we revisited this problem in the presence of a magnetic field. So now we have a transverse magnetic field, so a perpendicular to the direction of your graphene, to the electron gas. But we keep the same kind of structure. So we still in the diagonal of Schur instability configuration, and do we see what's happening? So this is the dispersion relation. I will spare you the details so you can check in the papers if you want. So this is the dispersion relation of this magnetoplasmon, if you want to call it like this. We prefer to call this a cyclotron mode because that's how we know it in plasma physics. And if you do this here, now the dispersion relation is parabolic, right? It's not linear anymore. And still, it's good because it's above the continuum. And now the solutions for K plus and K minus are given by like this. So if you solve for K, you get these two Ks here, K plus, AK minus, for the ongoing and forward going wave and the backward going wave. And this is the results from our simulation. And you can see that you can alongside with this longitudinal instability, you can also produce a Hall current. And this Hall current now has also growth in time, that instability in the Hall current, and then desaturates, and you have some DC current plus some AC current on the Hall current. And this is something that we are trying to understand. Probably you have some sensibility yourselves, trying to understand what we can do with this. So we are thinking about using or promoting some sort of Hall directional coupler device. When you have flow in one direction, you want to couple with other device in circuitry that is perpendicular, and this is something that we can in principle try to do with this scheme. Well, probably have another scheme, another application of it. I will be very happy to hear your opinions on these things. But this is for now, at least for a fact. So this happens in our simulations. We checked for different values for different range of parameters, and it turns out that you can excite this sustained Hall current that is just because of the magnetic field that you get. Well, it's not a surprise that we have a Hall current. What is interesting is that this behavior, so the growing of this linear growth plus saturation, also happens in the current. Yet we are not imposing any kind of boundary conditions. So along the transverse direction, the boundary conditions are free. So you can do whatever you want with this current that is produced here. Well, this is enough for the instability. Now let's focus on the viscose flows. So far in our hydrodynamic models, we have forgotten about these viscosity effects. But then in 2019 and 2020, so in the last 2 years, there are the two papers in Nature by Ku et al. And Sulpicio et al. Where have demonstrated experimentally that deviations from the so-called Poiseuille flow. So Poiseuille flow is this, if you have a viscose flows, from hydrodynamics, you have a pipe and you have flow in a viscose flows, the profile is more or less parabolic, right? So this is what Poiseuille's flows mean. And you see here that there's a deviation of profile. So the profile is non-monotonic and acquires these peaks here near the border. And you can really go from ohmic case to this parabolic, going from and on the middle you get this kind of very weird profile that is in principle not compatible with hydrodynamic models. So there in the papers, the authors claim that, or they offer some explanation in terms of electron hole recombination. Well, we try to do this. We try to see whether or not our hydrodynamic model would convey this message, and we came out with this model. So we use our model now corrected by this 1/2 factor here, and also with the fact that the mass that appears here is the local mass. So the mass that you get here, of course, the carriers are massless. But hydrodynamic mass is something that depends on the density. If you don't really remember, it's proportional to the square root of the density, right? I put in this in the first of the slides. I should have put it here. And now what we allow for this is just we use this viscosity here, viscosity term. This is the even viscosity, and we neglect for some odd viscosity for the moment. But this is the hydrodynamic model that we put in the computer. But the thing is, remember, so we keep this one half factor there, and also the fact that this m depends on the density local. So if you do this, what we get is exactly these profiles. So we could reproduce, in principle, the profiles that they have seen in the experiments, just by the fact that our model is compressible, not only at the level of the let's say the continuity equation, because it's something that you would expect for any electron gas undergoing electrostatic oscillations or electrostatic compressions at least. You would also get, if we also included the effect combined 1/2 and the mass here, and we see that you get exactly the same profile. So if you compare them, at least qualitatively, they look very well. And you can recover, depending on the aspect ratios of your system, the Poiseuille profile or these non-Poiseuille profiles here that they have observed in the experiment. So we are at a certain point excited to see that our hydrodynamic models, in principle, they are not very bad, because they can really do things that people observe. So we are trying to sell the fact that this is not exactly due to electron hole recombination. This is rather done due to the fact that the mass and to this pure hydrodynamic, let's say, is really stems from the hydrodynamical features that is inherited from the very dispersion relation of the electrons. So you have the Dirac cones. It changes a lot of things when you do the calculations from the Boltzmann equation, and that's life. If you deal with that at head and you put this in direct numerical simulations, in principle you can do a better job than with purely classical, let's say, or more phenomenological hydrodynamical models. And this we are happy at a certain point, and we wanted to investigate analytically why this is so. So Pedro came with this blasius equation. So this is the blasius equations, for those who are not familiar, are the equation describing the profile of a Poiseuille flow. In general, it describes this kind of profiles which are monotonic, but they don't describe these peaks, right? So this non-monotonic, these overshoots here in your profiles. So what we did is, Pedro and I, we were discussing this situation by taking into account this parameter here. So it's some sort of compressibility, along the flow, and we keep this nonlinear, this non-zero, we switch it on, and we modify this profile, this equation of this blasius equation, which is a third order differential equation, with these terms here now. So S is the local sound speed, and if U infinity is the velocity very far away from the borders. And you see that at least for one of the borders, for different range of parameters, these are the simulation results here in gray, and those are the solutions that come from the numerical integration of this equation. So in principle, this says that yes, so this is really a feature of a boundary layer. So this is really the feature of a boundary layer. You can really describe this with the equation. The things that we cannot control very well, so is the value of this beta. So what we did was to assume some reasonable values, and we see that it lies around at least our numerical simulation results lie here in the region where this beta remains small, right? So this is done for Mach 1/30. So this is a very small Mach number. Well, this is sorry. Oops, here, okay. So another aspect that we are trying to investigate with these hydrodynamic equations is the possibility of having the modulation instability in the flows. So if you start, so this is a picture in the 60s done for plasmas, and you see that in a wave, so let's say a flow like this, like as a rectangular flow, starts to have these modulations here. This is the famous modulation instability. And this is the spectral features of these modulation instabilities. This is something that happens, for example, in ion acoustic waves in plasmas. This is something that is very, very well known. And we try to, and we're trying to see whether or not this can be observed in our graphene plasmons. So what we are now doing is we are working with a more, let's say, a more complete model, including for these gated potentials, for the viscosity, odd viscosity terms, and magnetic fields. So U dagger here stems from the contraction with the velocity with the Levi-Civita. So it's just the off-diagonal part of the system. So that's why this viscosity here is dissipative, and this viscosity is the whole viscosity is something that is non-dissipative because it's off-diagonal, as you know. Well, then there is a method that allows to construct, let's say, mildly nonlinear solutions from these fully nonlinear solutions that we can control. This is called the reductive perturbation method. So we can really compute mildly, let's say, second order nonlinearities from this, and this is the equation that governs this. So phi1 here stems from the envelope of one of these quantities, let's say the envelope of velocity or the envelope of the density in your flow, right? It's a generic quantity here. And this is the equation that you get. This is a nonlinear Schrödinger equation, as you can recognize. So this is something that I'm very familiar with from in Bose-Einstein condensates. So this is something that we recover. Not only that, but also people who are familiar with nonlinear optics, they also recognize this equation immediately. So there's a criterion. By the way, omega 0 here is something that depends on the dispersion relation. So it's really the second derivative of the dispersion relation calculated in some point. And Q is another parameter that's very complicated. So it really depends. It's 3 or 4 lines of Mathematica that depends a lot on the parameters of your system. So this is the plot of this, so if you want. This is the Light-Hill criterion instability, which says that provided that this product is less than 0, you have instability. This amounts to say that if you have positive mass, you have instability if you have attraction, or you have instability for repulsive interactions if you have a negative mass, right? So this is what this Light-Hill criterion physically means. So in terms of parameters, let's say this omega 0 and magnetic field, those are the regions that we are expecting to have this dynamical instability in graphene, right? So in terms of this analysis, so what we are now currently doing, we are trying to check whether or not these instability regions that we can extract from this method are or not can be or not found are in the full numerical simulations, right? So we want to come from the hydrodynamic model. This is something that we have in the computer, and guided by these analytical arguments, try to see whether or not we can find this stability diagram that we have concluded here. Well, the thing is, of course, this is physically a very interesting aspect, and let's say just a physical, it's an aspect that interests people from nonlinear physics communities, but this is something that can be also important for some applications in plasmonics, right? So we have to keep attention. We are really trying to push plasmonics towards nonlinear stages and see what's going on there. Well, then there is a problem that we are also handling, which is the quantum kinetics. Of course, quantum kinetic equations have been around for almost 10 years or even more. There's in this graphene and Dirac materials. And there are lots of problems and controversies around these kinetic models. Galilean versus Lorentz invariance, electron relaxation rates. The calculation of these rates depends on many ingredients. There's a very beautiful paper of 2018, I suppose, where they derive these with very details. Then there's these problems with viscosity, and now more recently with Barry curvature. So there are lots of physics, new physics that you have to keep on when dealing with, if you want to really go to quantum in the formulation of your systems, right? How much time do I have left?
In principle, we are almost at 1 hour, so
okay. So I'll wrap up. Wrap up.
Coming to an end.
So there's still room for microscopic derivation, as I will try to convey, and this is something that we have constructed so far. So the Wigner-Moyal procedure is not exactly new. what is new in our work here is the fact that this term here, this kinetic term, is different. It's very different from what people do in the literature. And the reason is that because this kernel here is non-local. So for at all orders, you get this non-local kinetic term. So it depends non-local on your, operates non-local on your Wigner function, and depends on this kernel here. This is the so-called Wigner-Moyal equation for those who recognize. In the semi-classical version of it, you just get the Boltzmann equation, right? Actually, in the classical version, you get the Boltzmann equation. Or also for those who are familiar with optics, the so-called ray tracing limit of your kinetic equation. So this is something that we are exploiting in this paper. Of course, in the long wavelength limit, you recover the results that people usually deal with, which is this replaced by vk.nabla w, and you get this this correction. So at the formal point of view, this is the full operation that you have to perform in your quantum-kinetic equation. Of course, this is not very easy to work with, but you can do a few things. For example, there is consequences at the level of hydrodynamics. So far, you see that your equation now is not the classical equation, but you have an extra term in your current, which is the quantum current. So that the terms proportional to h bar that comes with this operator. Okay, so this operator, this symbols means that this gradient operates on the left and this operator operates on the right. So this is the so-called what we call as quantum current. The same for the equation of momentum conservation. You get the classical term, which is something that you get immediately from the regular procedures. This is something that you get from Boltzmann, right? And you can evaluate, you can even evaluate this exactly in zero temperature limit. But the other term here that you get is this one that depends on these operators and is proportional to the powers, to the odd powers of h bar. So this is really quantum pressure that appears here in these things. So the thing is, then in local equilibrium, if you have local hydrodynamical equilibrium, you can replace your Wigner function by this. This is the usual standard, the usual procedure. And from this, you can calculate so-called hydrodynamical mass. So what is the hydrodynamical mass? Is the term that allows for you to do from the average momentum to the velocity, right? Remember that in the computer, what you want is to put velocity. So you want to calculate velocities in the computer. For that, you really have to have something that allows you to go from momentum to velocities. And we do this with this hydrodynamical mass. This hydrodynamic mass is this complicated expression, but in the limit where T is much less than TF, you can get this correction here. Actually, a similar expression appeared in the paper in a paper in 2018 by Svintsov. The only difference, this is something that we don't agree with, is that they have a square root here, and in our case, we believe that the correction is really like this. So it's not a square root, but something like that. So this is something that we are still it took a while for us to understand, but we are very confident about this result now. And this is M here is the usual Drude mass that you get, right? So in these papers, in the usual classical models for graphene hydrodynamics, people just use this mass. So you see that you have a correction. There is a Lorentz-like correction to the mass when you have flow. Yes. Okay. Consequences of this is that this changes a little bit the dispersion relation of your plasmon. So you recognize the two first dispersions from the usual RPA calculations, right? So this is the usual square root term. The other one is this k-square term that it prevents repulses your mode from the continuum, and this is a correction now that comes with this term, and it comes really with this Drude mass, and it's proportional to k squared. So you see, this is something that changes a little bit the physics of your system. The same for your hydrodynamical plasmon dispersion for gated. So the correction is the same, but now if you have a gated system, your plasmon is linear, right? So at the low level, you have just the linear dispersion relation, which is proportional to this. Of course, this term is small, We don't have any hope to observe this in state-of-the-art experiments, but at least formally, this is something that is important to us to describe. So these kind of equations here that we are trying to devote some attention on in the future are the equations that will allow us to construct fully quantum hydrodynamics, let's say, or fully quantum transport equations, at least when including the extra ingredients like Berry curvature and so on. So the idea now, to conclude, sorry, I'm still, it's quite long already. This is the conclusion. So we can see that indeed we can produce this sort of terahertz harmonics with full electric injection. And in the future, what we are going to be interested in the near future, and this is something that we really hope to collaborate with you guys here in ICMM, is really to include this kind of terms. Let's start with a semi-classical approach for the moment, where you have now the effects of this Berry curvature in the dynamics of this thing. So if we redo all these calculations and we revisit all these nonlinear aspects with these ingredients, we suspect that many new things will and exciting things may happen here. Also, the other things that we are trying to do is to exploit the thermoelectric response of the system. So now together with the usual hydrodynamical equations, what you get is this equation for the temperature, and you can recognize here these two, the Seebeck and Peltier effects here, right, appearing here in blue terms, and the other term here due to this heat by Joule dissipation, right? So these are the models that we are now constructing and putting in our computer and seeing how far we can get. So this is just a preliminary result of this Dyakonov-Schur instability with this heat. And you see that in principle, there is some modifications. We are still facing some numerical model problems, so don't put much attention here. And also to thank our collaborators, Pedro here and José Figueiredo is our new PhD student, and João Pedro Bizarro, I couldn't find his photo, I'm sorry, who is our colleague there in Technico. So with this, I thank you for your attention and hope that we can keep some fruitful collaborations in the future. Thank you.
Okay, thank you very much, Hugo, for this very interesting insight, also for the outlook for possible applications. That's always, at least for non-experts, a very interesting part. The talk is now open for questions. So please raise your hand or write your questions to the chat. To start with, since, say, I'm a non-expert in this field, so the hydrodynamic equation, of course, contains some continuum limit. So what are, say, the limits on the physical system to, say, in size, or, for example, to for this approximation or for this approach to be valid?
Exactly. So typically, what you have to fulfill is the condition that typical size of your system has to be much larger than the free mean path of your electrons, right? So if you consider that the only electrons, the only ingredients for your collisions are electron-electron collisions, for example, then you have to be sure that the typical size of your system is much larger than the free mean path. So in practice, if you are above 109 nanometers or 1 micron, something like that, you are safe to apply these hydrodynamic models, right? So this is, in practice, this is what we have. Of course, this is really the continuum case. So mesoscopic systems, we are not really sure if this works. You have to pay attention to the details of you have to really have master very well the collision times and the free mean path of the system to understand when this is. So typically speaking, the criterion is that as long as this size remains small, you can ensure that you have local equilibrium. And in that case, you work with hydrodynamics.
Yeah, that brings me to a further question. So all interactions are contained in the collision term, I suppose.
Yes, this is the case, but then you can treat them at the mean field level. So yeah, if you treat the collisions at the mean field level, you get the equivalent of RPA of the Hartree approximation.
Yeah,
it's exactly the same.
And your equation contained other nonlinearities, but they come from the curvature of the graphene sheet.
Exactly. That's it.
Okay, more questions?
Maybe I can ask a question. Thank you very much, Hugo. This was it was really a nice overview and kind of inspiring to see that you're really pushing this field into this all electronics and plasmonics. One critical question is probably the boundary condition in order to really achieve these instabilities. To my knowledge, they have not been achieved so far. And I think one of the problems is the boundary condition, and the other problem might be that you also have this hydrodynamic regime that is, well, I mean, it has been seen experimentally, but it is not as easy as it would be needed maybe. And especially you need to kind of tune your system down to the Dirac cone. And then don't you think that you have to include the two bands? So you have to have the transitions from the valence to the conduction band also included. And then I also don't have seen so much the distinction between like a Lorentz invariant system as it is graphene and a Galilean invariant system, which would be the normal semiconductor. And I guess this might be also the difference that you have noted to the result by Swintsov, that he kind of, I think, always established the Lorentz invariant case. And I think in Dirac system, it must be Lorentz invariant. So can you comment on these several points?
Yes. In principle, so on a technological point of view, I think you're right. So in the sense that, so the boundary conditions that you can do are still something that it's under development. But we really believe that if you apply these infinite impedances at the borders and zero impedance at the other border, you can in principle work this out. So this is something, for example, we are trying to work with our colleagues in INL. Mm-hmm. So we are really working on this electronics to see how far we can get. Yeah, this is true. So it's not very easy to do these boundary conditions. The thing is, so relating the second question, I suppose, was the Lorentz invariance versus the Galilean invariance, right? Mm-hmm. So the way we see it is that in your dispersion, if you don't have Galilean invariance in your system, here you don't have Galilean invariance. And the fact that you don't have Galilean invariance stems in the fact that your boost, when you boost your dispersion relation with V0, is not V0 plus, it's not omega minus V0 S, V0K that you have, but you have this 3/4 here. And this 3/4 appears from this one half term that you have in your hydrodynamical equations. Right? You have to see that you are not exactly at the Dirac point. You have a Fermi level. You are away from the Dirac point in this case, right? So your Fermi level is not in zero. You are far away. You are well above the Fermi. Of course, very far away from the Brillouin zone, but still far away. So you are in more or less this kind of situation, right? We are far away from the Dirac point. So that's the reason why we have not included the holes. If you want to go down to value as far as KBT is comparable to the Fermi level, you have to take the holes into the dynamics. I agree with you, and this is something that in principle could be so giving the experimental conditions, real life experimental conditions, something that you eventually have to deal with. I agree with you. This is a limitation of our analysis. This is really a limitation of our analysis. So, but this fact here, this part here of the Swintsov mass, for example, mm-hmm. I don't think that you can really infer the fact that would get in his paper you have a square root there, right?
Which is from relativistics,
but it's wrong. That paper, it's wrong. If you two equations together, what you get is exactly this result. By the way, the equation is also wrong. So this is something that is a discussion that we have had with the editors and the referee, and their result is wrong. So eventually there is a typo there. So of course they saw this and they would see immediately. Of course we will expect this to be relativistic like. So the hydrodynamic mass of your system would get the same. But if you look at the paper, I can show you. If you plug there's a result. There's a sign. There's a square root problem there in the paper. Probably didn't notice because they were. That's the problem. They were so eager to see this that they immediately they assume that this to be the case. But even with their own calculations, if you follow their own calculations, you get this result. So that's the thing. I'm not really sure that they can claim. If you put the Fermi level away, that's the thing. Your system is relativistic, I agree, and it has Lorentz invariance at the single particle level. But if you put your Fermi level above, and then you do hydrodynamics with this local equilibrium imposed by a Fermi level way above from the neutrality point, I'm honestly not sure what happens.
Okay.
You see? So I think that's the thing. We can discuss this, and I think it is something that really deserves some discussion. But if I do hydrodynamics from a system that is for which the Fermi level is away from the neutrality point, I'm sorry, I'm not sure if we can guarantee that. You see, the equation says we can't, but probably there is something that we are missing here. I agree.
There's a further question by Mehdi Kargarian.
Yes. Okay. Thank you. Thanks for interesting talk.
Thank you.
So you mostly talk about, the hydrodynamic equations in graphene. So now I'm thinking about, use of 3D Dirac materials, and especially the wild-say metals, that the hydrodynamic equation will change in the presence of this chirality in the wild-say metal. Do you think that, including such terms would make much difference in, getting the Terahertz modes? Or
yeah, I mean, the thing is in 3D that there's different qualitative features from three-dimensional systems, right? The thing is, starting with three-dimensional systems, you have the plasmon frequency cutoff, right? Your plasmon gap, your plasmon spectrum is gapped in 3D. So if you have a gap, in principle, you have to rethink a lot about these equations. There's a lot of work in terms of derivation that you have to do to obtain these equations, right? So these equations really go from Boltzmann equation that has all the information about the bands, and then you calculate momenta and so on. You make these consistent tests all the time to check whether or not these terms appear. So this is from one side. So in terms of physics, let's say phenomena, I suspect that similar things may happen, but you just have to correct your equations. So you have to rederive your equations. Adding on that, okay, this is something that adds on, is between your question and the question raised by Tobias. For example, for two bilayer graphene, the hydrodynamic regime is exactly at the neutrality point. It's not when you have a Fermi level high, it's at the neutrality point. So in that case, the physics of electrons and holes will be very prominent, because you cannot, in that case, is very important. So I suspect that for this, all this phenomenology that we are discovering here has to be promoted with the two fluid models. Okay, and this is something that it can also happen in the case of 3D systems. I don't really know. Okay. So you really have to keep in mind. So as far as I'm concerned, in 3D models, I'm not really very familiar in the literature, but for what I've read, it's not clear which are the regions of parameters of temperature and densities where hydrodynamical regimes work. Probably you are more familiar than me. So I don't really know exactly what are the regimes where hydrodynamics approaches are valid. So there's some discussion that is needed before entering in these equations.
Sure. Okay. Thank you so much. Thank you.
Okay, I see no further questions. So let's thank the speaker and close the session.